Hello everyone, nice to see you again. Sorry for the slight delay. Okay, great. So we're going to continue talking about what we've been doing with these recursions. I'm just going to switch to the other way that I can draw all of these things. Let's go to this. Ooh, the blackboard looks too black today. Let me adjust that. 1 second. That might actually... I was giving a talk the other day, which might crash the system. We'll see what happens. Crop pad. Good. Does the system still work? Yes, I'm still here. So I didn't like duplicate. I heard that thing made its way onto the interwebs. Okay. So let's continue. Right. So we had found that there was some interesting formula for the Fibonacci numbers, and that's surprising that you can find a nice formula. But now let's go and try to do this whole thing in general. So it turns out that we can use the same kind of way to start to solve all kinds of these recurrences. To start with that, let's now start to do this thing in general. So suppose I have a recurrence, which is going where an is equal to, I guess I need some Greek letters or some other letters. A has already been taken. So I guess we can just use, I know, I'm going to use B and C. So B, A n minus 1. Oh, I know what I want. Just a second. I want to use capitals just so we can tell them apart. Capital B, A n minus 1. Plus capital C, a n minus 2. Okay? Suppose that that's the recursion that we're trying to solve. Now let's go and see if we can use the method that we just had to deduce a general way to go and solve these recurrences. Well, what should we do? Let's do this sort of like a review, in the sense that we're going to redo a lot of the things that we did earlier, except that now it's with B and C instead of 1 and 1. How should we set this up to begin? Can anyone give me some suggestion of what I should do to set this up to begin? Just like type raise hand is fine. Oh, yes. So, Jack. Matrix equation. Can you give me something that you might want to write as something equals something?
Well, I guess last time we had like n plus 1 and fn in the column, so
an plus 1 and an. That's a way to start. Okay. And I see that Venkatesh also raised his hand. Can you go and help me finish this? What else should I put? Maybe let's have 3 people involved. So, well, okay, maybe not 3 people. This one, Venkatesh, what should I do? This is an and an minus 1. No. Is it? Yeah, it is. Can you help me out?
I think it's like B and C, like, and then the same thing. There might be C.
Okay, this is hard. So, okay, here's what I always do. I just put some stuff down and I try it, okay? So if that was the case, what would I be trying to do in the top? I would be trying to do B, A, N. Is this good?
I think that works, yeah.
I think that works too. That is correct, right? If I do a matrix multiplication, I go grab this guy, whack it against that. It is exactly what I wanted. That is indeed equal to an plus 1. Hooray, it works. Okay.
One of them's probably 1, 0.
Okay, is it 1, 0 or is it 0, 1 is always the question. 1, 0, okay, this one I don't need to do scratch work. I just see I'll whack it this way, I get an. I'm happy, it's good. So this is true. Okay, so that's how we start. What should the next step be? This is like a review of the Fibonacci deduction thing. Anyone else? I have a matrix product. Braden.
well, now we can recur this in a general form in terms of the power of this matrix BC10 times whatever our first 2 terms are.
Okay, so we're going to take some power, okay? I like how you called it recur this. Usually I say recurse this, but recur sounds nicer. You're not cursing anyone. But so if I want this thing, I raise to some power. What power? Can you give me some actual numbers now? What should I do?
You could take it to the power of n, and then that would be multiplied by a of 1, a of 2.
Good. I like that one. I like that one because a lot of recurrences, a0 is nice. Or we want small things. Okay, so that's good. We've got this. So now what do I do? And this is like, we're shortcutting a lot of things now. It's like, what if I've got this like power thing, I need to do something to the power thing. I don't want to just take the power of the matrix. I want to find like this diagonal thing, right? And so now I need to figure out how do you go about taking this BC10 and then diagonalizing it. So if I wanted to do that, the way you do that is that we had to find some lambdas and some v's. V's are these 2 by 1 things, lambdas and v's, so that if I take this BC10 multiplied by the vector v, that was equal to lambda multiplied by the vector v. That was the heart of what we were doing. Because somehow if we found these things, we were then able to go and make some nice other matrices that I can multiply by. Actually, let me just write that down here before we go into actually finishing it. It's like finding some lambdas. Well, we're going to hopefully find 2 of them, lambda 1 and lambda 2. Last time those were 1 plus root 5 over 2 and 1 minus root 5 over 2. And the reason we want to find those is because if I got this, and I guess those should be called v1 and v2, if you found these things, then you were able to write down some kind of a equation. The equation you ended up getting was that if I took this BC10 multiplied by slapping together the 2 columns v1 and v2, we use the fact that when you multiply matrices, this is the same as if you just look at the results of multiplying each one vector by that matrix. And this was equal to the matrix where we know that what you did is you just rescaled each one, lambda 1 v1 and lambda 2 v2. You got this. And the beauty of that is that turned out to be the product of the v1, v2 on the left multiplied by a diagonal matrix on the right. Because when you do column operations, that's multiplying by the diagonal matrix on the right. This was times, I'm just always looking up to see if I have any headroom. I think this one maybe I'll make it. This is lambda 1, lambda 2. All of this I'm doing is true for all values of lambda and v. This thing is always true. The next part is not always true. The next part was where you took some inverse, right? The next part was to say, oh, this v1, v2 thing, if it's invertible, then I can invert it. So the next thing was important. If invertible, then you were able to just multiply both sides by the inverse of that, and you finally found out this nice form, BC10 is equal to, multiply that thing on the right, and we end up getting this V matrix, which we called P. We have this lambda matrix, lambda 1, lambda 2, and 0 and 0. And then you have the P inverse. And that is called diagonalizing a matrix. So this is called diagonalization. Okay, so then the heart of the problem became, gee, it would be great if I could find these lambdas and these v's, because if I can find a v1 and a v2 where I can invert that matrix, then suddenly I got this beautiful picture and we'll finish the whole problem. That was what we wanted. Now, that's also indicating why I'm not happy just saying, hey, I found a lambda and I found a v. I can get you another v, just double everything. If you have a v that works and you double everything, then that actually gives you another v that works. Because if you take your matrix times double of the vector, you just get double of the answer. But now you can also see why that's bad, because if I went and put v1 and double of v1 here, why is that not invertible? Can anyone tell me, like, there's some matrix fact? Like, if I write a 2-column 2 by 2 matrix and I have a vector, if I have two things, and if the other column is exactly like double of the first column, why is that not invertible? Subhashish.
One column is a linear combination of the others, so it's eigendeterminants so that is zero. But you could also think of it as like a transformation on both one-dimensional subspace. So
Yes. So there's lots and lots of different things that are around when a matrix has, is invertible or not. And one of the things is like if the columns are dependent, where you can get one column by taking a linear combination of the others, that's exactly what's going on there. And so that's why that one doesn't work. So that's actually how you know you want to find like these V1 and V2, which are like not just a multiple of each other. And we'll see some examples at some point in this class where that's actually harder to get. Okay? Okay, so now I know that my goal is to go find the lambda 1 and lambda 2. So how would I do this? Well, I need to now be able to know when can I find these v's where the v's aren't 0. Actually, the important thing here is that, if I wrote 0, 0 for the v, 0, 0 for the v, then that's really bad, because if you try to invert a matrix and the entire column is 0, you're not going to get an inverse, right? So that's actually why you know that you want to find this, so that this and the v is not just the 0, 0 vector. Okay, and what did we do to go about doing that? We now have this in terms of the BC10 times this v, and we want to get something that is not that is going to give us a v, something that I can solve, like a BC10. I'm seeking for a lambda so that I could actually find this non-zero v that works. Andrew. Yes. So this is actually part of like how you find these, how you diagonalize the matrix. I'm going to write that on the next screen. We had a BC10 multiplied by this v, and it was lambda. You can write lambda as this way, lambda and lambda, diagonal matrix. I like to use zeros in a different color so that we just see that they're insignificant. And then we multiply by this v. And now since you have v on both of them, now you can subtract. You can subtract that one over. And so I finally get that I want to know for which lambda is there a non-zero v. Non-zero, I want to emphasize, is not both 0. Non-zero v where I have b minus lambda, c, 1, and negative lambda multiplied by your v equals the 0, 0. Okay, and the idea here was this actually happens as long as the determinant of this is not 0. Exactly when the determinant of this b minus lambda, c, 1, and negative lambda is equal to 0. Okay, so now I just have to determinate this, and that is b minus lambda times negative lambda, and then minus a c equals to 0. Well, this is a quadratic equation now. So I guess we should just rearrange what we've got. And if I see what happens, I get, I'm going to rearrange it into a lambda squared minus lambda b minus c equals 0. Okay, so that's kind of satisfying. Remember the equation, that the recurrence we were trying to deal with. The recurrence we were trying to deal with, I'm just going to write here. Remember, it was an is equal to b an minus 1 plus c an minus 2. Isn't that nice? It's like this b and c up here, and this b and c up here. So it's like, it's even easy to remember. Unfortunately, some people just remember it. I prefer to know how to get it. In fact, I am always afraid that I remember it wrong, because it depends on how you're labeling this. Is it like b an minus 1 plus c an minus 2, or is it b an minus 2 plus c an minus 1? If you ever forgot, it's easier just to like do the matrix multiplication, quickly get this, and it pops out. Okay, so now I just need to know, like, are there any lambdas that make this the case? Here's where I want to drive home one other point. Something I said many times on the last lecture, and maybe the one before that, was that as long as I get two distinct solutions for this lambda, if I find two distinct solutions for the lambda, I'll get v1 and v2, which are not just rescalings of each other. Let me emphasize that here. Note if you have that lambda 1 not equal to lambda 2 are both solutions, meaning to this, let's draw something here, to this thing, if both solutions to this, then the resulting, that was supposed to say resulting, V1 and V2 are not rescalings of each other. And the reason why that's true, I'm going to emphasize again, is since if you happen to take any matrix, this was the BC 1, 0, if you take this and you multiply it by, for example, twice V1, if you tried to rescale it, then if you had a rescaling, then the answer here would actually be exactly equal to twice of what happens with the BC 1, 0 times the V1, which we know is twice times, lambda 1 times the V1, because that's what it means to go and, when I multiply the matrix by the V1, I get the lambda 1 times the V1. Oh, but that's equal to just the lambda 1 times twice the V1. So what I'm emphasizing is, if you just rescale the vector, then if you take matrix times the rescaled vector, your matrix effect is the same effect. It's just like multiplying by the same lambda. So what that means is, so if you rescale the vector, effect of multiplying matrix is the same as before. I'm saying the effect as in like multiplying by the matrix scaled you. You scale by the same thing. You scale by the same lambda 1. And so if I had two different lambdas, then that means that they have to give you very different v's, because otherwise if they gave you like a rescaled v, they would be the same lambda. Did that logic make sense to people? We will actually do this even more intensely with like 3 soon. Okay? So we've got this thing. Now we know we just need to know, like, are there two different ones? And what if they're the same? That's going to be a funny special case we'll have to deal with later. But what if they're different? Suppose I found they're different, because we're about to get a big theorem. So suppose they're different. Suppose that this lambda squared minus lambda b minus c, I'm going to flip the lambda b. I want to call it b lambda, because now it looks more like a quadratic. Okay? It's the same thing. If you wrote lambda b, it's still the same. But it's just like lambda squared minus b lambda minus c equals 0. If that has two distinct solutions, then you're really happy. So I'm going to rewrite this equation, lambda squared minus b lambda minus c. So if lambda squared minus b lambda minus c equals 0 has two distinct roots, then, well, let's say the roots are lambda 1 and lambda 2. What do I get? I get something really exciting. I suddenly found out that if I take this particular BC 1, 0, this to the power n times your A1, A0 is nothing more than just taking a certain matrix P multiplied by this lambda 1 to the power n, lambda 2 to the power n, 0, 0, multiplied by P inverse. Oh, sorry, multiplied by A1, A0 at the end. So what? We're almost done with getting a complete solution to AN. What happens next? Maybe to prompt what happens next, let's remember, this is AN plus 1, AN. Braden.
We do blob math
Blob math. That's right. It's time for blob math. Very relaxing. So this is just equal to, well, what's this stuff? These are blobs. This is a blob with two blobs. I mean, this is a vector with two blobs because these things, blobs don't depend on n. So what's going on here is that if I write a blob equals independent of n, just a constant. Okay, so if that's the case, then all I have to do is I just have to go and do some more blob math. What happens next? This guy here, this is where you get, I want to make sure people are following. So what would this be? Jack. Jack? You might be muted. Oh, I can't quite hear you. So you might be muted, but we heard you earlier. So please check your microphone because we know we can hear you somehow. But I'm going to guess what you were going to say. What you were going to say was probably blob lambda 1 to the n. Need more space for that. Blob lambda 1 to the n, blob lambda 2 to the n. Okay, and then now if I want to multiply that by p, well, p happens to be blob, 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 blob. So let's just write that down. And if you multiply all of this together, finally what we get is a n plus 1 a n is equal to, well, we got some blob stuff. This is actually only 2 vector. It only has 2 entries in it. But it's blob lambda 1 to the n plus blob lambda 2 to the n and blob lambda 1 to the n plus blob lambda 2 to the n, emphasizing here that this is only a column vector, not a 2 by 2 matrix, not a 2 by 2 matrix. Okay. All right. How do we then work out what is a formula for an? We basically have a recipe at this point. So what do I do? How do I find out an now? Subhashish.
You just pick 2 values which are convenient and use them to calculate the bottom blobs.
Yep. Use 2 convenient values of n so that, or just 2, to compute the constants, let's call them alpha and beta, in the a sub n is equal to alpha lambda 1 to the n plus beta lambda 2 to the n. And that's it. So we actually have now a complete way to solve these linear recurrences if you had only 2 things involved. These are the linear recurrences, which happen to be of the form a sub n plus 1. Let's just remember what these were. These were a sub n is equal to b a sub n minus 1 plus c a sub n minus 2. All you do is you just go and write down that quadratic equation, find the roots. If you're so lucky that the roots are different, then this works. Then you just like do this simple thing we did last time, which was do it with a1, do it with a0, solve for the alpha, solve for the beta, boom, you're done. And that's the end. Okay, now if you're not so lucky, if they're the same root, that's something else. We'll talk about that later. In fact, actually the homework, which I need to post, the homework will probably have, I think it has a problem where you go and play through with these matrix multiplications of what happens if you actually have the same root repeated twice. But is this clear at this point? Like this is how you go about solving, linear recurrence of this form, where you just have a sub n and the 2 previous things? So this is like powerful. It's like every single thing. Like if I had an equals 50 an minus 1 plus 2 an minus 2, bang, there's a way to solve it. You just like make the equation, you solve it. And actually, the probability that you get 2 repeated roots, if you chose a random like b and random c, the probability is actually 0. So every time you see two repeated roots, that means that the person making the exam just kind of intentionally gave you something with repeated roots. It's actually, in the real world, it's unlikely to get repeated roots. With this, I want to now move into like, how would you do this if you had 3? So this general area, by the way, is an area called homogeneous linear recurrences. And homogeneous just means that if linear means that I only have the power 1. I'm not going to like multiply a's with each other. And this is like a 3 term. But I'm going to do with 3. I'll just write with 3. Okay, with 3, let's try this one. A sub n is equal to capital A times a n minus 1 plus capital B times a n minus 2 plus capital C times a n minus 3. Okay, suppose I want to know a general way to solve these. This is called linear because I only have the power 1 on each of these things. Homogeneous means that I don't have like plus 5 at the end. Sometimes people talk about linear functions of like y equals 3x plus 2 as a linear function. But that plus 2 is a little bit weird because it means that your y-intercept is not 0. Homogeneous would mean that you have a 0 y-intercept. Homogeneous generally means that like everything being 0 works. Okay, actually homogeneous doesn't really mean that. Homogeneous means that all of the powers are the same. And if you had a constant, like the power of a's in the constant is to the power 0. But here everything is to the power 1. Okay, how can we do this? Now we need to work harder. Can anyone give a suggestion of how you might do this? Probably going to start in a similar way, but we have to be a bit more careful soon. Andres.
So it's going to be pretty similar, but this time we'll start with, we can have a 3 by 1 vector. So a sub n plus 1, and we can have a sub n and a sub n minus 1.
Okay.
And then we'll have that equal to a 3 by 3 matrix.
Now we have to work. What in the world? And then what do you multiply this by?
The top row, I think, should be a, b, c.
Okay.
The middle row will be 0, 1, 0. And I think the last row should be 0, 0, 1.
Okay, and what do you multiply this by?
This will be by an minus 1, and an minus.
Okay, let's check. So we always go and check. So the first thing that you get on the top thing is going to give you go and grab the whole vertical thing and you whack it against the row. And you get capital A, an, plus capital B, an minus 1, plus capital C, an minus 2. And that is in the form of what I'm looking for, right? It's A times an A something plus B times the A previous plus C times the A previous. So that is indeed equal to A n plus 1, exactly what you wanted. Let's check the second row. The second row tells you that you took these 3 things and you multiply, you whack this against that, only the 1 stays. So you get A n minus 1. Maybe we want to make a slight edit.
Yeah, I think we should shift the 1s over to the left.
Okay, that's no problem. And again, that's how we discover something. Every time I do this stuff, I go and, I actually literally just like write things down and try it, and it's like, oh, it didn't work. If it didn't work, we make it work. And so now it works. This is an. And the third one, let's check. No, yeah, that's right. The third one I check, take this thing, whack it there. I should pick up the an minus 1. I am happy. It works. Okay, so that is true. And then the next thing I would need to do is I need to go and grab this guy, and I need to find some way to write it as some power, right? So now I could write the whole thing as ABC (1, 0, 0, 0, 1, 0) to the power n multiplied by, we always like to the power n because that's easier to do like powers for. Power n minus 1 just gives you all this like lambdas to the power n minus 1. So it looks ugly. So what should I multiply by? Can anyone give me what to put here? I still want like this thing here. What can I do to finish this? Braden.
I think it would have to be A1, A0, and A negative 1.
Yeah, sure, why not? You can have a negative 1. An plus 1, an, an minus 1. Whenever you have a recursion, you can always describe a negative 1 to be whatever it should be to make the recursion true. That is true. If for some reason you prefer to not have a negative 1, you could do this just by shifting this a little bit more. But actually all of this will work, and just for the sake of showing you that this would work, let's leave it as it is, okay? Because actually there's a lot of flexibility in how you solve these things. Because the heart of it is actually in figuring out how to do the exponential of this ABC 1, 0, 0, 0, 1, 0 to the nth power. So now let's go to that. Next page, I need to worry about ABC. So I have this A, B, C, 1, 0, 0, 0, 1, 0. I need to do nth power of it. So I need to start thinking about like this thing times these v's equals lambda times a v. Okay? I need to solve for these things. And why it's useful is because if I find 3 of them, okay? So let's just write down like, if I find 3 of them, 3 lambdas. And I'll even say 3 lambdas that are different. We'll worry about repeated things later. That are different. Then what you get to do is you can say that this ABC 1, 0, 0, 0, 1, 0, and then you just multiply it by slap all 3 of them together. So it's like V1, V2, and then V3 slapped together. What happens here? Why is this nice? We're now doing like 3 by 3 multiplication. But when I do the matrix multiplication on these 3 by 3s, what do I actually get? I'm thinking that these are V1, V2, V3 with corresponding lambda 1, lambda 2, lambda 3. Can anyone help me finish this one out? Venkatesh. Yep. You just rescale all of them. Lambda 2, V2, lambda 3, V3. And I just drew it with a bit more space because I knew that these are getting longer. And these are all columns. And again, if you're ever curious, like, does that really work? Is that how you multiply matrices? Just think of how you'd get those columns. Like, how would you get the middle column of the output? Well, you just grab the middle column of this guy, whack it against the top, and then you take the middle column, whack it against the second, middle column, whack it against the bottom, and you see that everything you've done just used the middle column of this piece. So that's why the answer is just what would have happened if you pretended there weren't any other columns at all. So it's nice to know that. But now, the magic was to notice that that happens to be the same as if I take the V1, V2, V3, original ones, and these are columns, and I've got to multiply that by a diagonal matrix. And this diagonal matrix happens to be the diagonal matrix, which is just lambda 1, lambda 2, lambda 3. Actually, what I wrote here is true even if I found the lambdas which are the same. Oh yeah, by the way, these are zeros, so these are all zeros outside. Okay, and even if I found lambda 1, lambda 2, and lambda 3 that are the same, this is still true. However, the next step is going to get interesting. The next step will be like, I'm going to be able to take an inverse, okay? And how do I know I can take an inverse? I'm now going to not be able to just say, well, one of them is the sum of the other two. That's like messy to deal with. Last time we just said like one is a rescale of the other. We could deal with that. The next step is, in order to know that I can invert this, there's one fact from linear algebra that says, well, as long as I can show there's no linear combination, no way to take a constant times the first one plus a constant times the second one plus a constant times the third one, as long as I can show there's no linear combination of these that's 0, then it's invertible. So let me write that next. To invert the V1, V2, V3, it's enough to know that there are no no like non-zero linear, no non-zero coefficients that give you a linear combination that makes all the v's go away. So there's no, let's give these some names, C1, C2, C3 constants, not all zero, such that C1 V1 plus C2 V2 plus C3 V3 is equal to 0. And these are as vectors. I'm realizing I should probably have continued to write. Actually, I'm gonna draw this again where I really draw the v's as vectors. So I'll write such that C1 times this V1 plus C2 times this V2 plus C3 times this V3 is equal to the 0 vector. I know that in most matrix classes you draw like little arrows over the vectors. I personally always like to draw them as the rectangle shape because then I just can see like what's the shape of it. Okay, and this is like what it takes to show, well this is actually equivalent to being able to invert a matrix, is that there's no way to find this. How do I go about showing that? I want to use the fact that the lambdas are all different. And these, I want to say like here, these particular v's happen to be where I've gotten this matrix guy, and the matrix guy multiplied by a v just rescales it by that particular lambda. Well, now let's suppose I've got this. Suppose I've got this nice equation. Is there anything I can do to this nice equation to try to show? Would it be 3 rows of zeros for the sum? Shanai, what do you mean? I don't completely understand. What do you mean? Oh no! Yes, I know what you mean. Okay, oops. Yeah, the 3 by 3. Sorry, it's 3. It's not 0. Okay, yeah. Thank you. We're in the world of 3 now, not the world of 2. 0, 0, 0. Thanks for catching me on that. Okay. Yes, answer to your question. Yes, absolutely. And please catch me whenever stuff like that happens. So now I need to go and show that, like, if I had this thing, the C1, the C2, and the C3, they're all 0. What can I do to show that? All I know is that if I take the matrix and I multiply it by a V, by like V1, then I happen to get, lambda 1 times the V1. How can I do this? Raise hand. Andrew. Or did I read that right? Andrew.
Yeah. Gauss elimination is an easy way to do it. So it's basically just like solving the system of linear equations.
Yes, so I could go and try to do Gaussian elimination, that's true. But what I want is I want a theoretical thing where just the fact that the lambda 1, lambda 2, and lambda 3 are different, I want to just use that one fact to go and show that, whenever I have different lambda 1, lambda 2, lambda 3, then this is actually going to happen.
Oh, well, since like they can't be like scalings of each other, like if they weren't different, then they can't be like, then you can't have two vectors that are like a linear combination of the other ones.
So you definitely can't have that one is a scaling of another one. That is definitely true, right? One is not going to be a rescaling of another one. On the other hand, I don't yet have a way of proving that somehow one of them isn't a sum of the other two. Yeah, so there's still like some more that we have to do here. Jack?
We still can't hear you.
Oh no, we can't hear you, Jack. I don't know what happened. We could hear you the first time. Maybe hit both sides with the ABC matrix. Yes, what else can we do? We have one piece of information where you take this matrix, multiply it on the left, make it on the left, multiply by the vector, then it like scales stuff, right? So yeah, we have one piece of information that's useful. Let's go and use it. So if I have this thing, okay, well, let's suppose we're supposed to show that whenever you have this thing, not all 0, show there's no way to do this. Prove by contradiction. Assume that I have C1, C2, and C3 multiplied by this, giving me 0, 0. Assume that for the sake of contradiction. And then let's see what happens. Okay. Well then, assume for contradiction that what I have is that I do have C1 times this vector V1 plus C2 times the vector V2 plus C3 times the vector V3 that actually equals 0, 0, 0. Assume we've got this. Well, then I don't know anything else I can do. Left multiply by the crazy matrix we've got. So then, if you just took left multiplied by the crazy matrix you got, actually it works out well because you get to use the distributive property, and you end up getting that if you left multiply it, it's C1 times the matrix. Let's just call it M, okay? So I'm going to have this so many times that the M is the matrix, which happened to be ABC 1, 0, 0, 0, 1, 0. That was M. C1M, whenever I have a constant, the constant always just like factors out to the left side, times V1 plus C2 times the M times the V2 plus C3 times the M times the V3 equals 0, 0, 0. Can anyone help to simplify this a little bit? Oh, people could hear, but it's really quiet. It's saying. Yes, you can. So what we found out is that C1 times lambda times V1, plus C2 times lambda 1 times V1 times lambda 2 times this V2, plus C3 times the lambda 3 times the V3 equals the 0, 0, 0. Okay, that's neat. What else can I do? So I have these lambdas, I've got these V's, I've got these C's. I happen to know that if I took this V1, V2, V3, and then I suddenly have this thing also, this is also true. How can I use this to kind of deduce? Subhashish.
Subtract it from the others, then you can get that one vector has to be a scaling of the other.
Yes. What I can see is that you're solving some system of equations here, which is cool. Like what you're doing is you're solving a system of equations. I'm trying to think of the easiest way to try to say this. Yeah. So you were saying like you want to just like solve a system of equations where you multiply this guy by lambda 1, and if you multiply this whole thing by lambda 1, then you end up getting some interesting equations where you take this guy and minus that guy. Is that what you're saying?
Yes.
Yes. So for example, I mean that is one way to do this. So let's just do this because we are a little bit short on time today. We'll use this thing and we'll show how it generalizes later. If I assume this guy for the sake of contradiction, well then let's take that first guy and multiply both sides by lambda 1. Okay? If you multiply by lambda 1 on both sides, then I get C1 lambda 1 times the vector V1 plus C2 lambda 1 times the vector V2 plus C3 times lambda 1 times the vector V3. That's equal to the 0, 0, 0. Okay? Now you wanted to subtract because you said let's at least get rid of this like lambda 1 V1 stuff. So if I take these two and I subtract, then I get an interesting equation. I get C2 times lambda 2 minus lambda 1 multiplied by V2 is equal to C3 times lambda 3 minus lambda 1 times V3. Oh wait, what did I do? No, it's plus, not equals. Plus V3 equals the 0, 0, 0. Okay, and this is somehow telling you that one of these must be a multiple of the other. Sort of. It depends on how. Oh yes, and people are saying we could use induction. Yeah. So the thing is, this is actually related to a very important determinant, which we'll get to next time as we go and generalize this thing. But this thing here, this is almost correct. When I say it's almost correct, what we're saying is assume for contradiction we have these things, and I should have said like the C1, C2, C3, C3 are not all 0. Right? We're assuming that, not all 0. Now, if I have these things, as long as I know that both of these coefficients are not 0, then I've just found out that v2 and v3 are rescalings of each other. Wait a second. How is that a contradiction? Just a second. Yes, what exactly we're trying to prove is a very good question. So I'm trying to get to that too. Thanks for asking that question. Right? What exactly we're trying to prove? We're trying to prove that if the 3 lambdas are all distinct from each other, then these 3 vectors are linearly independent. So we're going to assume that the 3 lambdas are distinct. We'll assume that we have one of these equations, which is this thing, which is all 0. We're trying to prove that the C1, C2, C3 are all 0. So we're assuming for contradiction, I happen to have this thing here, and that the C1, C2, C3 are not all 0. And we want to find some contradiction, which is like they're all 0. So going over to here, how are we getting that? I don't think we have it yet.
Don't we know that they're not rescalings of each other already? From like it's the same argument as before.
Oh, that's how we know it. Okay. So you're saying... Yes. So what he's saying, this works. That's why I said this is a bit more complicated than what I was going to do, but this works. What he's saying is like, oh, we already know that the v2, v3 are not rescalings of each other because the lambda 2 and the lambda 3 are different. That's what we did for the n equals 2 case. Right? We already know that these two are not rescalings of each other, these v2, v3. So we already know that lambda 2 not equal to lambda 3 implies that v2, v3, that's supposed to say v2. Well done. v2 and v3 are not rescalings. And that one we had last time, because if they were rescalings, then they would have the same lambda thing connected to them. And so suddenly what you find out is, if these two are both rescalings, what did you just conclude? Well, I have that lambda 2 is not lambda 1, and lambda 3 is not lambda 1. So I've got two things here which are not 0. That's very powerful. So if I suddenly found out that I have two vectors which are not rescalings of each other, but a constant times the first one plus a constant times the second one equals 0, what do I conclude? It's very powerful. Isain. Yes. Yes. You want to get a contradiction here of like the trivial solution, which is like, look, if C2 and C3 are both 0, then this is possible. Right? If C2 and C3 are both 0, then even though these two vectors were not rescalings of each other, well then 0 times it plus 0 times it is 0. Right? So the important thing you get out of this is if I have two vectors which are not rescalings of each other, and they're each multiplied by something, but the answer when you add it all together is 0, the only way is that the coefficients are both 0. That's the only way. Okay? Not rescaling, so the coefficients are both 0, but importantly, the lambda 2 minus lambda 1, that's not 0. So that means that the C2 is 0. So let's to finish this thing, what we have here is, so the coefficients are both 0, and so the C2 is equal to 0, and the C3 is equal to 0. Well, now if I know that the C2 is 0 and the C3 is 0, what else do I know? Well, if I go back to the first equation, C2 is 0, C3 is 0, so C1 times some vector, which is not all zeros, is equal to the all zeros. That tells you that C1 is not 0 either. So back from the original equation, using, let's put a star, using star, C1 is equal to 0 also, contradiction. So this is actually one way to prove that if I had the lambda 1, lambda 2, lambda 3 all distinct, then actually you automatically are going to have that the v1, v2, v3 happens to be an invertible matrix, because there's no way to go and write this linear combination, so it's called, to get the all zeros. And this is an example of how, like all of these proofs, there are many different ways that you can go about and cut this, and this happens to be one of the ways, and it's nice to be able to see that everything is consistent. That then tells you that you can diagonalize the matrix. Diagonalize the matrix in the sense that you can take this inverse. And so where we'll continue from next time is next time we'll go and figure out, now that we know we can diagonalize this matrix, well, then what are these lambda 1, lambda 2, lambda 3? Comes from some formula, and we'll do that next time. Great.
Thank you.